Oh hey, I didn't see you there. Today we'll be learning about the wonders of molecular geometry, and we'll be studying section 6.5 of the text. Our objective for today is to explain how the shapes of molecules are accounted for by the hybridization theory. So first of all, we need to know the definition of hybridization before we can start our objective, which is the mixing of two or more atomic orbitals of similar energies on the same atom to form new orbitals of equal energies. Methane, or CH4, provides a good example of how hybridization is used to explain the geometry of molecular orbitals. Methane's going to look a little something like this, with one carbon atom and 4 hydrogen atoms. The orbital notation for carbon shows that it has 4 valence electrons, 2 in the 2s orbital and 2 in the 2p orbital. Through experimentation, we know that methane has a tetrahedral geometry, and that's formed from the 2s and the 2p orbitals, both of which have different shapes. So we're going to take this carbon atom and we're going to show you guys a model of carbon's 2s valence electrons filled in the orbitals, and then the 2 other valence electrons filled in 2 of the 3 2p orbitals. It's all good. To achieve 4 equivalent bonds, carbon's 2s orbital and 3 2p orbitals hybridize to form 4 new equivalent orbitals called sp3 orbitals. Now we're going to refer back to the model again. The superscript 3 in sp3 indicates that the 3p orbitals were included in the hybridization, while the superscript 1 on the s orbital was understood, because it simply went from the 1 carbon stage through hybridization and remained, while the 3p transferred over. The sp3 orbitals all have the same energy, which is greater than that of the 2s orbitals, but less than that of the 2p orbitals, as shown in our model here. All equal, greater than the 2s, but less than the 2p. Oh hey, forgot you were still there. Now we're going to go on to hybrid orbitals. Hybrid orbitals are orbitals of equal energy produced by the combination of 2 or more orbitals on the same atom. Oh, you're still here? Let's get back to our lesson. Sorry, I just had to quench my thirst for a second. So, the amount of orbitals produced, all 4 of them in the sp3, are equal to the amount that were originally combined, the 1 from the 2s and the 3 from the 2p. So all 4 of these are simply equal to the amount produced. It's pretty simple, huh? Oh, hey, I didn't see you guys there. Was not expecting you. I wasn't just... So, we're going to refer back to the book to finish our lesson. So why didn't you get a shot of this? This model right here explains how the amount of the type of atomic orbitals, sp, type of hybridization, sp, number of hybrid orbitals, 2, makes a linear geometry with a 180-degree angle. Our methane model has an sp3, so it has 1s with 3 p's for the atomic orbitals, 4 total hybrid orbitals, because it came from the combined amount to the produced, and that's why we have a tetrahedral shape for methane. So this is a great model on explaining the geometry of hybrid orbitals. That's going to conclude our lesson on hybrid orbitals for today. Now that our lesson is over, I can say we had a good time today, learning all about hybridization, hybrid orbitals, the geometry of orbitals. We definitely learned how the shapes of molecules are accounted for by the hybridization theory. I just want to say, chemistry rocks.